All right, so we're going to look at a few new terms, and the first one is something that we've done problems with, but we've never actually defined it. So the universal set U is the set of all elements in discussion. And this is kind of vague, but whatever problem we're working on, we only want those elements to exist in certain problems. And so we're going to call that our universe. Nothing else exists outside of that universe. Secondly, the complement of A bar, or A prime, is every element not inside of A. So everything on the outside of a set A is its complement. And you'll see both of these notations depending on which book you use, with where you look online. We will use primarily A bar. I think in older assignments, if I ever put an old exam up or something, it might have A prime. So let U, our universe, be A, B, C, X, Y, Z. And then we're going to define set A, set B, set D, set E, and set F. And so what we want to do here is find A bar, B bar, F bar, D bar, B union D, and B union D bar. And so instead of bar, I could have said complement for all of these, A complement, B complement, and so on. So remember that A bar, A complement, is everything outside of A. So A is A, B, X, Z. So we're missing a C, and we're missing a Y. And remember, it is a set, the complement, and so we need those curly brackets on the outside. B complement is going to be A, X, and Z inside of the curly brackets. F is the empty set, and so its complement is going to be the universal set. And we can think about the converse of that. The complement of the universal set is going to be the empty set in any occasion. D complement, everything outside of D, so that would be the set containing C, X, and Z. Now B union D, the set containing A, B, C, and Y. And now we want B union D complement, and that's going to be the set containing X and Z. Now we do want to be careful because notice that bar is over top of the entire B union D. If it was only over the B and the D, and not over that union, it would be something completely different. And that's how we end up with De Morgan's laws, actually. So another definition now, the cardinality of a set A is the number of elements in A. And we primarily use sort of like the absolute value bars around a set, and that's going to denote its size or its cardinality. But you might see N of A, again, from time to time or wherever you look online, different older books. So example, let set A be the set of letters in the English alphabet. And so the cardinality of A would be 26. And if we have B defined by A, B, C, D, E, F, 1, 3, 5, 7, and R, if we count those, we're going to get the cardinality of B is equal to 11. And kind of a weird question here, and we're not really going to answer it just yet. What's the cardinality of Z? Or I could say, what's the cardinality of Z plus? There's a lot of different things I can ask there. But we're not really prepared to talk about that quite yet. So a definition. The power set of a set A is the set of all subsets of A. So this is where we start to grow sets quite a bit, and they start to get larger and larger. Our notation for a power set is going to be the scripted P of A. So that means power set of A. And let's just look at a really basic example. Set A is defined by X, Y, and Z. So if we want the power set of A, we're going to have to consider every single subset So that means the subsets that have no elements, one element, two elements, and then finally three elements. And that way we can keep track of them pretty well. So first we will consider zero element subsets. And there's only one of those, it's the empty set. Remember that the empty set is always a subset of any set whatsoever. Now, one element subsets, we'd have the set containing x, the set containing y, and the set containing z. Now we want two element subsets, so we'd have the set containing xy, the set containing xz, and the set containing yz. And then lastly, this might be the easiest one, three element subsets, that's just going to be A itself, the improper subset. And so we're going to take all these things and put them inside of even larger curly brackets, and that's going to be the power set of A. And so one thing to notice here, this doesn't usually happen in mathematics, but if we look at the cardinality of A, it's really 3. And the cardinality of the power set here, we'd have to count up every subset and we end up with 8. And so a natural question to ask is, how are these going to be related? More specifically, if we know the cardinality of A is equal to n, what's the cardinality of the power set of A? Alright, so in Calc 2 or Calc 3, if you've taken those, you probably have seen these symbols before. R2 and R3. And these are going to be the set of 2D and 3D spaces, respectively. So really, R2 is just a set of all ordered pairs, with x and y being real numbers. And R3 is the set of all ordered triples, where x, y, and z are real numbers. So the reason that we're looking at this is we want to fully understand where R2 and R3 come from, because we're going to use something pretty much the same. So R2, we can really write that as R cross R. And R3 is really R cross R cross R. So if we want to think about what R2 physically represents, it's going to be R cross R, so that's just two real number lines. And so what do we want to do with those? We want to cross them, which means that now they're going to be perpendicular to each other. And that's how we end up with the x and y axis. Now R3 is going to be three real number lines. And when we cross them, R cross R cross R, they have to be perpendicular to each other. And that's how we end up with three-dimensional space. So if we have A cross B, two sets A and B, it's going to be every possible combination of ordered pairs with the first coordinate being from A and the second coordinate being from B. So as a really simple example here, we're going to let A be 1, 2 and B be xy. And so this is what A cross B would look like. We'd have 1x, 1y, and 2x, 2y. So that's it. All right, so a few things to think about. First, if we know the cardinality of the power set of A, we asked that just a few minutes ago, what is the cardinality of the power set of A? So we're taking that question one step further. Secondly, what's the cardinality of the empty set? And third, we're going to consider again the positive integer z plus. So this set is a finite Well, it's an infinite set. It's not finite. And when any set is equivalent to z plus, we call it denumerable. Now, equivalent really just means that they have the same cardinality, the same size. But if you think about what it means to be equivalent to an infinite set, that might be a little bit weird, because how are we going to count if it's infinite? And again, whenever we hear the word denumerable, we want to think same cardinality as z plus. So if you look this up online, you might see the same cardinality as n, the natural numbers, which is fine. That's just the positive integers including 0. So we want to know now which infinite sets are denumerable. Which of the sets that we know about has to be infinite? Which of the sets that we know about are going to have the same cardinality as z plus? Now, if we think about the real numbers for a minute, the real numbers contain all of those positive integers already, and then there's infinitely more on top of that. So the real numbers are out just logically if we think about that. So what other sets are there, and how are we going to know that they're definitely denumerable, definitely equivalent to z plus?